Hello, and thank you for tuning in to the Group Theory Podcast. My name is Logan.
My name is Michael.
And today we're sitting across from Dr. Stephen New, Professor Extraordinaire here at the University of Waterloo in the Department of Pure Mathematics. Dr. New has won numerous awards, including the 2012 Award for Distinction in Teaching, and he coaches the Waterloo Putnam team, going above and beyond to offer extracurricular contest preparation workshops. And without further ado, how are you doing today, Professor?
I'm doing pretty well. I have a little bit of a cold like everyone does at this time of year. Otherwise, I'm fine.
We're all recovering, There's a nasty flu going around in the U.S. apparently, which kind of sucks, but hopefully it doesn't spread over here. But,
hopefully.
That's just the winter for you.
Yeah, exactly. Well, it's been pretty nice lately, except for the rain and water, but I'm happy with the temperature.
Yeah.
All right, well, let's just jump right in then. So the first question we have is, what's your field of research, and how would you kind of describe that to a non-math person?
Well, I haven't actually been doing research for 15 years, but before that my field of research was differential and algebraic geometry. And as far as how I would describe it to a non-mathematical person, it depends a lot on how much time they had to listen to my explanation and how interested they were. But for a very short explanation, I'd say it's the study of curves and surfaces and higher dimensional versions of those.
Okay. So algebraic topology, that's algebraic structure, not algebraic topology, algebraic geometry. So that's algebraic structures on geometry, not like arithmetic geometry, for example.
So algebraic geometry is the study of algebraic algebraic objects that you can describe as being zero sets of polynomials.
Okay,
so most of the algebraic, let's say the geometric objects that you're used to from high school, like parabolas and circles, they can be given an equation, and that equation is a polynomial equation. For parabolas and circles in the plane, it would be one equation in two variables. For a sphere, that can be represented as the solution set of a polynomial equation with three variables, say x squared plus y squared plus z squared is the radius squared. And an algebraic variety is a geometric object which can be described as the solution set to some polynomial equations. And algebraic geometry is the study of the links between the geometry of these objects and the algebra that you can obtain by working in the polynomial algebra, the algebra of polynomials.
Interesting. Okay. So I assume you develop algebraic objects on top of this. I'm just trying to distinguish this between algebraic geometry, and we talked to Professor McKinnon earlier about arithmetic geometry, which sounds like a similar field from how you're describing it. So describing geometric objects as sets of solutions to polynomials. So how would you describe the difference between the two? How would you differentiate algebraic geometry from arithmetic geometry?
Arithmetic geometry, I wouldn't go into any difference between the two, I guess.
Oh, okay. I see. Just different kind of approaches to the same ideas.
And the algebraic geometry that I was doing would be complex algebraic geometry. So I was mainly working over the field of complex numbers. In differential geometry, you often work over the field of real numbers, but you can also work over complex numbers.
Okay.
And then there's a very close link between differential geometry and algebraic geometry working with complex numbers.
Right. Okay. When did you decide that mathematics, and specifically the mathematics that you studied, was the career path that you were interested in?
I didn't ever choose my career path. I just allowed fate to push me around wherever it wanted to. I liked studying math at university, and so I kept on going and studied math, did some graduate work, and I ended up teaching math courses and liked it and continued.
All right.
I didn't ever have any kind of goal or ambition to become a mathematician, and I didn't aim for it deliberately.
It's interesting that you say that, because a lot of the people we've interviewed so far have that exact same answer, that they just kind of somehow ended up as a mathematician working at a university. But can you talk about some of your experiences at university for math? Did you have a particularly favorite course, or what led you specifically towards algebraic geometry?
So I started out at the University of Waterloo. I was an undergraduate student here at Waterloo, and I started out in physics.
Okay.
I was a physics student, and I didn't like all of my physics courses. I liked some of them, but not all of them. And as a physics student, I also took a few math courses And I usually enjoyed my math courses more. And I left physics in my 4th year. I sort of dropped out, finished a 3-year degree, went traveling for a while and came back to do a math degree. And the courses that I enjoyed were the more theoretical ones, so I took pure math and finished off a pure math degree. And then when I went to do a master's, I wanted to do something that was related to both math and physics. And so I went into differential geometry, algebraic geometry, because differential geometry is used in a lot of theoretical physics, like general relativity. And the algebraic geometry that I was working in had relevance to physics, not really applications to physics, but it was relevant to some equations of physics, in particular to the instanton equations, which are a slight generalization of Maxwell's equations. And they were being played with by people who were trying to look for some kind of unified field theory, some way of linking quantum physics together with general relativity. And in these theoretical studies of physics, people work in differentiable manifolds, which have curvature.
Yes, yeah.
Okay. You're kind of famous around here for being the contest math professor. So we're wondering, when did you kind of get into contest math? Was it always an interest for you?
I suppose I always liked doing math contests. So when I was a high school student, I did write the math contests that were put out by the University of Waterloo, and I enjoyed writing those contests. As a physics student, I didn't write any contests. When I switched into math, I wrote the Putnam contest once. I didn't do particularly well. I'm not one of the good contest problem solvers. In pure math and other departments as well, there are a lot of very good problem solvers. I'm pretty mediocre as a mathematician. But I like math contests, and I always enjoyed them. After I finished my PhD, I went to Thailand. I went to university in Thailand. I was a professor at a university in Thailand for about 3 years. And in Thailand, I helped to train the Thai Math Olympiad team. And then when I came to Waterloo originally because my father's health was bad. So I came back to just be close to my father, who lives in Waterloo, or lived in Waterloo. And when I came to Waterloo, I just asked them if they had some teaching jobs for me. They didn't have a tenure track position at that time, but they had some teaching jobs and hired me on as a sessional teacher, and I taught some courses. And a few years later, Christopher Small, who was the Putnam coach or the Putnam supervisor at Waterloo, he'd been doing it for 15 years, and he thought that was long enough. And he just held a meeting for anyone who was interested in helping with the Putnam training, and I attended the meeting, and I was really the only one at the meeting. So by default, control of the Putnam team went over to me. And then I took over the training of the Putnam team after that.
Okay, interesting. Okay. How would you describe the experience of coaching the Putnam team?
Well, I like it. I like
That's
it.
a start.
I guess I'm officially called the Putnam coach. I don't actually do any coaching. I don't coach the Putnam team. I don't take the team members and teach them how to solve math problems. I just provide a whole large collection of math problems for students to work on just recreationally. I call these things recreational problem solving sessions.
Yes, yeah.
And I don't do any coaching. I don't teach people how to solve the problems. I just give the problems to the students, have the students work on the problems for fun. I enjoy working on the problems myself. I find it entertaining. And if students have questions, they can come and ask for questions, or they can ask for hints. The actual training they get, I think, just comes from taking math courses, particularly the advanced sections of our core math courses. Those courses provide enough mathematical knowledge that they can do things like the Putnam contest.
Now that's an interesting opinion, because I've always considered the advanced sections of the math courses to be more oriented towards pure and research level math, and there's always been a distinction in my mind between what you consider research math and what you consider contest math. Whereas you think that doing the advanced sections of the math courses actually makes you better prepared for contest level math. So what were your reasons for that, do you think?
depends on what kinds of contests you're talking about. But I'm thinking particularly of the Putnam contest, which is a very challenging contest.
Mm-hmm.
And for a lot of their problems, you require some theoretical mathematical knowledge. So they might have a contest problem which maybe involves differential calculus, but they won't have problems where you just have to solve a derivative or optimize a function.
Yes, yeah.
A lot of their problems do involve a theoretical knowledge of limits, and it helps to have learned rigorous proofs of some of the theorems in order to approach those problems. So there are advanced sections which do cover a lot of theoretical math, which is useful in pure math. Those courses, I think, are useful specifically for the Putnam contest.
I see.
And most, maybe all the students who perform well on the Putnam contest do take a lot of pure math pure math courses as well. So it's useful to have theoretical math in order to do the Putnam contest. There are other math contests, say the high school level math contests, which don't really require any kind of theoretical mathematical knowledge. So it really depends on what kind of math contest you're talking about. You talked about the difference between research skills and problem-solving skills for contest problems.
Mm-hmm.
And there's most definitely a difference. But I would say that people who do well on the Putnam are almost guaranteed to be capable of doing good mathematical research.
Okay.
But the converse is not true. People who do badly on the Putnam can still be very good researchers. And it is a very different skill, because when you're presented with a math contest problem, you know in advance that it's going to have a nice, short, elegant solution. And when you're presented with problems to do research on, you don't know in advance whether the problem you're wrestling with has any solution at all. And you don't know if it has a short solution or a long solution. And so research requires kind of prolonged concentration for a long duration, weeks or months or even years, whereas contest problem solving is quick.
Right.
So yeah, they're not identical, but there's a definite correlation.
Right.
Now I wonder, you said just a couple minutes ago there that you enjoy working on like the Putnam problems and like all the contest math problems. So I wonder, as someone who's gone through all of university, gotten their PhD, works in mathematics, works in academia, how difficult would you find like just a standard Putnam test as compared to, say, someone, obviously second year or third year doing the Putnam?
Well, for me, they're difficult, and I usually do try to solve them as I'm sitting down. I'm supposed to be supervising the students, but I'm not allowed to answer any questions. So what do you do when you're sitting there? Students are writing. So I usually try to solve the Putnam questions, and usually I can solve about 3 of the 6 in the morning, 3 of the 6 in the afternoon. Sometimes only 2, sometimes 4. And if I were to write up my solutions, I would not be as good as the best undergraduate students in the university. The best undergraduate students would beat me. I don't know what place I'd get. I might get something like 5th place amongst undergraduate students. The best students would beat me. I'm not as good as the best students. And I'm also not as good as the best faculty members. Some of the faculty members, they wrote the Putnam when they were undergraduates. Some of them, did well, maybe getting honorable mention, placing in the top 100. And I placed outside the top 200 when I wrote it.
Oh, okay.
So I didn't do particularly well.
Well,
I'm definitely not qualified to be the Putnam coach, but I do it anyway, and I enjoy it.
All right, well, I'm glad you enjoy it. And you certainly had a lot of exposure to students that are very good at writing the Putnam contest. So what do you think, what would you say you've observed to be the best qualities in a contest taker or a problem solver?
Well, first of all, I think probably they're just more intelligent than the rest of us. And
that's disheartening.
Yeah.
I think there's actually a large difference in intelligence between the great mathematicians and the mediocre mathematicians. I think the difference is quite large.
Interesting. Okay, so
but you can train yourself as well, and I think the way to train yourself is by just doing problems. If you just sit down and you work on challenging problems, then slowly you can train yourself to gain the ability to solve more difficult problems.
Right. So you think that it's not necessarily innate? Some people have a better intuition or a better natural intelligence, but it can be learned. the problem.
Yeah, I think it's
abilities.
both. Yeah,
Okay.
I think it's both. I think
Okay.
I think probably there's some genetics involved.
Yeah.
And probably some people are just more naturally genetically intelligent. But intelligence is very difficult to measure, and it's very difficult to decide how much is genetic and how much comes through nurture.
Right.
And I mean, there's probably a lot depends on your first years of development as well, when you're not even 2 years old and can't even speak. Probably those things have an effect as well.
Right.
But once you get up to the university level, I think you can improve your intelligence by just wrestling with difficult problems. And if you do that often, I think you can train yourself to become more intelligent than you would have been otherwise.
All right. Well, that's reassuring.
Yeah.
Thanks for answering that.
Well, do you have any then strategies then for people who are working on contest problems, or anything in particular that tends to help people train themselves, like you were saying, in order to get better at problem solving over time?
So again, I don't really coach people. I don't really help people to get better. If you want to get better at contest problems, you're not really going to learn from me. But I think you can get better just by practicing problem solving. You can pick up books on problem solving, or you can just look at previous Putnam exams and just try to solve them. And I think by solving many problems, I think students do improve. And probably most of the students who do very well on Putnam did train themselves by working through previous year's Putnam contest problems. I think that does help. I don't have any particular skills that would be useful for every student, but when I see these Putnam problems and I play with them myself, usually my first thing that I do is I try to play around with small examples. If I'm trying to prove something is true for a large value of n, I just play with the problem for small values of n, and sometimes that helps you to see what kinds of patterns are involved. So playing with specific cases is probably a good general strategy that often helps with many problems.
Okay.
Now, in your experience with contest problems, is there any one that stands out in particular in your mind? Like, do you have a favorite contest problem?
I guess the answer is no. I don't have a favorite problem. I have lots of problems that I like. I can't really pick out any particular favorite.
Is there anything that comes to mind off the top of your head, something you were working on recently that intrigued you?
I guess nothing particular, no.
Okay, fair enough.
You can, again, look back at previous Putnam problems, and you can look at many problems, and you'll find many of them that are very entertaining. And I can't pick out a single favorite.
That's okay. Yeah, I guess there's just a lot of favorites then. But I do want to ask, how much of a community is there around problem-solving math and contest-style math versus research-level math? Because I wanted to ask questions about some famous stories in contest-level math, and I was wondering if there's like a big air of talk about problem-solving and things like that.
I am not in that circle.
So there is a circle,
but I think there probably are. So there are websites with problem-solving groups.
Yeah.
Like the Art of Problem Solving is a well-known website for people interested in problem solving, and you can go there and join chat groups.
Right.
And I haven't joined any of those groups, so I'm not involved in that conversation. But I think you could join that.
Okay.
And there are research-level mathematicians who enjoy contest-type problems, and the problems that they work on are their contest-type problems. You can find a lot of toy problems that you can solve, which sometimes have short, clever solutions.
Right.
And there are mathematicians who do concentrate on those particular kinds of problems. So you can work on problems that are similar to contest problems as a mathematician.
Yeah.
I don't know if this, in high school you've got the Euclid, university you've got the Putnam, the Special K, these math contests. Are there math contests for actual, mathematicians who...
Not that I know of.
Probably all too busy.
But as I said, I think there are mathematicians who approach mathematics as if they're doing problem solving. They like to find many, many small problems and solve them just for their own entertainment.
How much camaraderie or competition is there between research level mathematicians? Like, is there competition between mathematicians to find the shortest proof that pi is irrational or transcendental or something like that, or things like that?
I don't think so. So I'm not a research mathematician. I'm not doing research, but I don't think researchers usually feel a strong sense of competition. I think they work together and they share their ideas, and they often discuss ideas with colleagues, and they don't usually hide away independently like Wiles is supposed to have done to look for his proof of Fermat's last theorem. But usually they'll talk to colleagues and share ideas. I don't think there's a competitive feeling amongst most mathematicians.
Okay. Now, the reason I wanted to ask about if there's an air of, or if there's a community around problem solving is because I've heard a few stories on sites like Math Overflow and things like that about particular methods that have become sort of folklore in the problem solving community. So, like, are you familiar with like the whole thing around Vieta jumping when that was invented?
No, I haven't heard that term.
Okay. There was just a big, it's kind of become folklore in the problem-solving community, as far as I can tell, because it was on, I think, a Putnam, but it might have been another contest, and no one could solve it, or it was the Math Olympiad.
Yeah.
Yeah, it was Math Olympiad.
Yeah, it was the IMO. I think it was like the problem number 6, like the famous.
It was a problem that no one could solve at the contest there, and even the people who invented the problem didn't have a good solution to it, and then eventually someone found this thing called Vieta jumping, which made it like 5 lines. So the reason I bring that up is I kind of wanted to ask, do you have any personal stories like that, or have you encountered any methods that have become sort of folklore in the problem-solving world?
No. You probably know more about problem-solving folklore than I know about.
Okay.
And I'm not usually clever enough to come up with any really remarkably nice, neat, short solutions. Occasionally I'll find a solution that pleases me, but usually I'm not one of the clever ones.
Well, that's okay. Yeah, so long as you get enjoyment out of the problem solving itself.
Yeah, exactly.
Yeah, no, I agree with that.
Yeah.
Well, do you have a favorite theorem?
Again, no favorite. Lots of favorites. Maybe a kind of a vague answer to that is that I tend to enjoy theorems that appear to join two mathematical disciplines or cross between disciplines.
Those are always beautiful, yeah.
So maybe one of the first ones you'd see might be the Galois correspondence, right, which has a nice correspondence between the fields and groups.
Okay.
And then in algebraic geometry, there's a lot of such correspondences. So the fundamental group would give you a correspondence between topological spaces and groups. And these correspondences are sometimes described by using the language of category theory. So I often like theorems that jump between two different branches of math.
Okay. In your mathematical career, do you have a proudest moment or a proudest mathematical achievement?
I suppose I don't have many mathematical achievements at all.
It doesn't have to be achievement in the sense of a worldly achievement, just a personal achievement.
Yeah, my greatest achievement, I suppose, would have been the results of my PhD thesis. So I came up with some invariants for certain kinds of vector bundles, holomorphic vector bundles, over projective space crossed with a disk, and wasn't completely original. It was extending some invariants which were found by my supervisor, and his invariants were for rank 2 bundles, and I extended those, and I made variations on that so that they would apply to higher rank vector bundles and vector bundles with other structure groups. So that would have been my main mathematical achievement, the main original thing that I accomplished that other people hadn't accomplished. Otherwise, occasionally I've just solved very small problems or come up occasionally with a different solution to an existing problem.
Okay.
Okay.
One thing, you mind if I ask?
Yeah, go for it.
Yeah. So there's, I noticed, and something that's always struck me that's interesting about you, when I talked to you while you taking your 145, you were teaching 145. is that you seem to have a very broad knowledge of mathematics. Like I asked you about the Banach-Tarski paradox, and you said, no, I don't know much about that, and then proceeded to tell me about it in terms of free groups and things that I would have never thought about. And so it seems that you, correct me if I'm wrong, but it seems that you enjoy like the broader aspect of mathematics and exploring all the different directions that you can go in it. So do you feel like you're that type of person, first of all? And then second, do you feel like that's more beneficial in the greater scheme of things to being a research level mathematician, or should you focus? Should you have a real magnifying glass on whatever it is you're studying?
I guess you asked a few questions there.
Mm-hmm.
So I definitely have broad interests in the sense that I don't have only one favorite kind of math.
Okay.
So my research, I said, was in differential and algebraic geometry, and perhaps things that are geometrical, maybe I could say, are my favorite kind of math. They tend to be geometrical, but I like all branches of math. I enjoy them all, and I'm not a researcher, I'm a teacher, but in the Department of Pure Math, I always tell the chair that I enjoy teaching a whole variety of courses, and I like to have the chair assign teaching to other people first, and then just take whatever's left over and assign that to me, so that I get a wide variety of different kinds of courses to teach. And I enjoy that, and occasionally I teach a course that I don't know a lot, and I have to learn some material in order to teach the course. So I enjoy that. I enjoy learning the material that I need in order to teach the course. And maybe that gives me a bit of a broad exposure to different branches of math. It's usually not at a very high level, so my mathematical knowledge that you talk about as being broad, it's not really broad at a very high level. It's broad enough that I'm able to teach, say, any of the undergraduate courses in pure mathematics, but it's not broad at the graduate level, and my graduate level knowledge is more specifically in differential and algebraic geometry.
Mm-hmm. Well, I think it gets harder the higher up you go, because then each individual field breaks off onto one branch and then another branch, and it becomes so focused on one thing, and then there's so much information about so one dense. Tiny thing.
Yeah. You asked me, perhaps as a strategy for a graduate student, should you focus in one discipline? And I don't really know the answer to that. I think the answer that it is more necessary nowadays to focus in one area in order to be able to work your way out to the ends of those branches, the tips of the branches of the giant mathematical tree.
Mm-hmm.
And gone are the days when people understand all of mathematics. You can't possibly understand all of mathematics. There's too much for any one person to understand. So you have to specialize in order you to work your way out to the outer tips of the branches to make an original contribution. But I think the greatest mathematicians do have a very broad and very wide knowledge, and they often do find connections between different branches of mathematics.
Mm-hmm.
So it's useful not to know only one branch. It's useful to have a broad knowledge of different branches of mathematics, but nonetheless you do have to focus on one specialized area in order to make it out to the outer branches, the current research level.
Right.
So I don't have a good answer to your question. I think you need to do a bit of both. You need to specialize, but you need to learn as much as you can about other branches of mathematics as well.
Yeah, it's interesting because we were interviewing Dr. Forrest. He was like our first interview, and he was saying that you can become so specialized that talking to another mathematician that's got a different field of interest could be like just gibberish back and forth, and it's almost impossible to understand each other just because of how focused it becomes. That the math and the tools you use in one area are completely different than the math and tools you use in another area.
Right. Yeah, he would know. He would know. But often there are very good mathematicians who can traverse these subject areas.
Okay. Well, moving on then. Who do you have any like mathematical heroes like from history, mathematicians that you just look at with awe?
Yeah, I suppose so, but not different than anyone else's. I mean, if you go back, you can go back to Euler and Gauss and Riemann.
Yep.
And they're physicists who did a lot of mathematics. There's Newton, who was apparently an unpleasant person but great mathematician.
Yeah.
And Einstein did a lot of mathematics in his work, and Dirac. A lot of physicists are also mathematicians.
Yeah.
Maxwell would have been a mathematician as well.
Yeah, yeah.
And in my branch of mathematics, the differential and algebraic geometry, there were people like Poincaré, and in more recent times, I suppose Michael Atiyah is a great mathematician in recent times.
I'm not familiar with the name. What's he study?
Well, he did a lot of stuff in algebraic geometry.
He was algebraic geometry.
And I mentioned that in my PhD thesis I was working on some mathematics that was related to physics, and in particular there's a correspondence between certain holomorphic vector bundles and certain solutions to the instanton equations. And that was one of the contributions, one of the many mathematical contributions of Atiyah, is he worked on this correspondence between vector bundles, which are in the domain of algebraic geometry, and solutions to the instanton equations in the domain of physics.
Interesting.
And his papers there would have been one of the few cases in which a mathematician has used mathematics to solve a physics problem. Usually the flow goes the other way. The physicists solve their own problems, and then in the solution they play around with some new mathematical ideas that get thrown over to the mathematicians who work with those ideas and develop them and make them more rigorous.
Yeah. You go ahead.
Thanks. So you were talking about how all these physicists were actually doing mathematics and how they could be considered as mathematicians. And if you look at high-level theoretical physics, it looks like applied math. Do you draw any kind of distinction between, say, an applied mathematician and a theoretical physicist who just works with equations all day?
Well, I think there's no sharp line. There is no sharp distinction between the two. Yeah, a mathematician in today's academics, a mathematician can be the same thing as a physicist, and vice versa. But I was saying they were the same thing if you go back to Newton's time, because I expect the word physicist hadn't been invented, and so he would have officially been a mathematician. But what he did would be considered both mathematics and physics.
Right.
But I don't know when the word physics was invented, but I don't think it wasn't likely to be invented back then.
Interesting. Okay. I was just going to say, I was going to agree with you that I think it's always amazing to see what ideas spawn out of physical ideas and then spiral off and become things that you can actually do in mathematics or prove things in mathematics. Like something I was reading about recently that was interesting was called the Dirac sea. Have you heard of the concept before?
No, I don't know what that is.
I don't know very much about it at all. I just recently found it out. But it's this idea of like an infinite sea of particles with negative and positive energies and things like that. But the physical interpretation, it'd take too long to get into it. But the reason it's so interesting is because this physical idea is used to prove a fundamental result in combinatorics, the triple product, the Jacobi triple product, which is like seemingly completely unrelated to this idea of particles bouncing back and forth in a Dirac sea or whatever you want to call it. So I don't know, it's just something that I was reading about recently that I found very interesting, and is a cool example of how physics can spawn really interesting mathematical ideas. Yeah,
there are other similar kinds of situations like the Witten invariants that come from physics and then are studied afterwards by mathematicians and put into a more rigorous context. But a lot of mathematics that we would consider pure mathematics, and we're supposed to be interested in it as pure mathematicians purely for its own sake. But often the mathematics that pure mathematicians are interested in do have some relevance, for example, in physics.
Absolutely. I think there's a feedback. It starts in physics and mathematicians develop it, and then that becomes useful in the physics side of things, which further develops physics. And it's just, I think the two are much more intertwined than I think some pure mathematicians realize and take for granted. So it's always very interesting to study the two.
What was a big shock to me was how big of a splash random matrix theory, which is deeply rooted in physics, is making in analytic number theory now with the L functions and the zeta function, and just how this thing that's really useful to physicists, and that the physicists I don't completely know the history, but I believe, if I'm not mistaken, that the physicists developed these concepts on their own, and then the number theorists were like, oh, hey, this is actually kind of useful. And so something that came out of physics is being used completely in math, and I think that's another really interesting example of how physics doesn't get enough credit, I don't think.
Yeah, absolutely.
You mentioned that Brian Forrest was saying that sometimes mathematicians can become so specialized they can't communicate clearly with each other. The same's definitely true between mathematics and physics. Pure mathematicians and physicists, sometimes they'll be working on ideas that are related, but they won't always notice the relationships because they're using different languages. And then there are a few people who can converse in both the two languages and they can relate information back and forth.
Yeah, there's a few famous examples of that happening. I can't remember any off the top of my head.
Well, Professor Mararu, she was telling us in her interview how she went to a conference recently between mathematicians and physicists, and the whole point was to say, okay, we've got these problems. Is there any way we can, work on them together? And it's really
I think it's a good idea.
Yeah,
of course. I think they're way more intersected than people think, than people understand.
Yeah, no, and I think once communications become easier between the two disciplines, both will take advantage and gain from communication.
Mm-hmm. Now, something we always ask mathematicians, the people that we interview, is do you see mathematics as more of an art or as a science? And as an extension to that, what about problem solving? Do you see problem solving as more of an art or a science?
I don't have a good answer for that one. I think it probably varies a great deal on who's doing the mathematics and what they're doing it for. And I think both are true.
Okay.
Depending on who's doing it and why they're doing it. So mathematics most definitely is used as a tool by many people, including engineers. Many people who would call themselves mathematicians, say applied mathematicians, are interested in taking mathematics and applying it as a tool to solve various real-world problems. And pure mathematicians would tend to treat mathematics less as a tool and something that you build and play around with for its own sake.
Mm-hmm. And problem solving?
And problem solving, I think, again, the very intelligent students do have a knack for being able to just reinterpret problems and in a different way, so that they can, by thinking of it in a different way, they can come up with a solution. And I think probably for those students it would be very difficult for them to explain exactly what their motivation was. And sometimes they'd have a very intuitive way of motivating their thought process, which you might consider to be artistic.
Okay. Now, actually, just going back to the contest math problem, because I just thought of a question off the top of my head here. Can you talk a little bit about the process of creating a contest kind of problem? Because, I mean, on one hand, you want it to be solvable in a reasonable amount of time, but you also don't want it to be too easy or have the tricks too visible. Can you talk about at all the process of coming up with a good contest problem?
Well, so for me, when I come up with contest problems, I come up with them, I suppose, in various ways. So one way is by reading a math paper and noticing something in the math paper that could be formulated as a contest problem.
Okay.
Sometimes that can be done, and I expect probably that's done by other people who make up problems as well. Maybe they find a problem in their own research, or they find a problem in a paper where one small part of that research paper can be reworded to make a good contest problem.
Like a specific case of a theorem or something like that?
Yes, or often it would be part of a proof of a theorem.
Okay.
Okay.
That's really interesting.
I remember reading about one problem solver who their method was to take just a simple fact that was something a curious identity, for example, or something about whatever, and encode that somehow into the problem in a way that you needed to dig through the interpretations of the problem to get to the real meat, and then you realized, oh, it's equivalent to this one simple little fact, So
Yeah, so sometimes you take the fact as your starting point,
Yeah.
and then you think of a way of twisting the interpretation so that the fact becomes more hidden, and there's a key to unravel it.
Mhm.
But sometimes the same thing happens if you're trying to prove something in a theorem. Sometimes somebody's trying to prove a theorem, and they have to reinterpret their way of thinking about the theorem, to reinterpret it in a way that makes their problem solvable as well. So sometimes you do it in the other way, so that they need to find the key to unravel the problem that they're actually working on, rather than finding the key to hide the source of their problem.
Yeah.
It goes both ways. Also, when I'm making problems, sometimes I come up with problems when I'm thinking of assignment problems. Making up contest problems is not that different from making up assignment problems. If I'm making up a problem for, let's say, an advanced section of a math course, I'll often think of many problems, and sometimes they're too difficult, sometimes they're too easy. But sometimes when I'm thinking about an assignment problem, I might think about one problem which ends up being, I think, maybe too difficult for my homework problem, but maybe it's good for a math problem to put on a contest. So sometimes they'll pop up when I'm looking for a different kind of a problem.
Okay. Is there a good way to gauge how, like, you come up with a problem, is there a good way to gauge how difficult it will be? Because I know, working on assignments, sometimes I'll see something that Michael doesn't see, and it's really easy for me, and it takes him 5 hours. So is there a way to gauge just from the problem whether or not it's going to be a good, difficult problem, or
well, not for me. So certainly, if I just ask myself the question and I don't know the answer yet, then for myself, I usually can't immediately, unless it's a question which I can look at the question and immediately know how to solve it. If it's that kind of question, then I'll be able to gauge the difficulty. But if I'm thinking of a question and I don't immediately know how to solve it, then the answer is no. I can't tell in advance if it's easy or difficult. And for myself, I have to sit down and try to solve it first. And only after I've worked out a solution do I know if it's easy or difficult. And even then, as you pointed out, I might be mistaken, because maybe the solution I came up with was a difficult solution, and maybe there's another easier solution. And I miss that. And sometimes when I've made problems, like in the Big E and Special K where I make the problems, I have occasionally made a mistake and put on a problem out of the contest that I thought was reasonably difficult. And then some of the students solved it by an easy method.
Okay. Mm-hmm.
So that has happened. I've made mistakes. When I make the contests in advance, instead of procrastinating it and make it at the last second, sometimes I'll take my problems and give them to another faculty member. Often Ken Davidson is my guinea pig. I give them to Ken Davidson, and Ken Davidson will solve them quickly. He's a good problem solver. And sometimes he'll detect such errors. Maybe I have a problem that I think is difficult because my solution was difficult, and he'll solve it easily and give me a comment and say, maybe this one's too easy. I solved it very easily. But I would say usually, once I've solved the problem, I have a good sense for how difficult or easy it is. But not until I've solved it.
Fair enough.
Yeah, absolutely. So I guess we're pretty much almost out of time here. So we've got one last question, and that's just, what advice could you give to us aspiring mathematicians who one day want to be working in a university, lecturing or doing research? Or
nothing. I have no advice for you. I'm not qualified to give you advice. I have no advice. My advice is be good to other people. Don't make other people sad. That's my advice.
Oh, that's good advice.
That's a great.
Maybe just enjoy the mathematics. So whatever mathematics you do, my advice is to try to take pleasure in it. If you're taking a course and the course seems boring, remember that that's never the math that's boring. You can go and learn more about the math, and every kind of math is interesting. And I think you should just take pleasure in what you do and try to cause no harm to other people and other creatures.
Well, great. That's very optimistic. Yeah. Thank you. That's some great advice.
Okay. Well, thank you very much for coming on the show.
Well, thank you for coming in to interview.